this session we'll discuss momentum. But before we go there, let's look at a few simple examples based on finding center of mass, what we have learned so far. So let's say you're given a rod of length L. So if this rod has uniform mass density, that is, if the mass is uniformly distributed throughout the length of this rod, then you know that its center of mass will be located right at its center. But this rod has variable mass density such that the mass density, which is linear mass density, varies as x plus x square from one of its ends. And we wish to find the center of mass of this rod. Right, so let's say that this linear density is given with respect to the left end. Right. So first of all, looking at the expression, we can see that as we move further away, the rod starts to get denser, right? Because as x increases, x plus x square will start to increase, right? So, we can expect that the center of mass will lie at a point which is further than L by 2, right? How can we say that? We can say this because we know that center of mass should lie closer to the region where the mass density is high, right? So since it is higher to the right end, as we move closer to the right end, the density is increasing. Hence we could say that more mass is towards the right end of this rod, and hence we expect that the coordinate of center of mass should be greater than L by 2, right? So now to solve this, since we have a variable density, what we need to do is take elements, very small elements where this variation can be ignored, right? So let's take an element at a distance x and of thickness dx. Now we know that even on the small element the density should vary, but the element is so small that the variation is negligible. So we can say that over the small length, this mass density remains constant, right? So if that is the case, then the small mass of this element, which we know can be given by lambda into its length, which is dx, right? So we see that dm becomes x plus x square dx. So this is the mass of this small element. Once we have this, the rest is fairly obvious. We know that x coordinate for center of mass should be integral of x dm, right? So x into dm, which is x plus x square dx, upon the entire mass. Now, since we do not have the expression for entire mass, even that has to be integrated. So in the denominator, we'll write it as integral dm. Now dm we've already found is x plus x square dx. And once again, the next thing to do is to decide the limits for dx. So you can say that x will vary from 0 to L, because once again we'll start taking elements from this end and then we'll take all the elements up to the last end, to the last point, that is the other end, right? So the limits for x are 0 to L, right? So the integration is fairly simple. The first term becomes x square, so that will yield you L cube by 3, plus this term is x cube, so that will yield you L raised to 4 by 4. Similarly, in the denominator, you'd have L square by 2 plus L cube by 3. So now, you can take L cube common from the numerator, and so let's take the least multiples that can be taken out. So L square from the denominator and L cube from the numerator. So you would have something like 4 plus 3L by 12 into L cube divided by 3 plus 2L by 6 into L square. So this gives you the final answer that XCOM is equal to, you'll be left with 2 in the denominator and L in the numerator. So it is 4L plus 3L square divided by 6 plus 4L. Right, so this is the coordinate for center of mass. Now there is one thing, a slight thing to notice, that you may think that this does not make sense dimensionally, right? Because lambda is equal to x plus x square. It kind of does not make sense dimensionally. So we could assume that there are some constants present which have dimensions, right? So in case that thought came to you, we could say that lambda is equal to x plus x square has some constants here which have value 1, but they do have dimensions, right? So moving on, let's consider another problem. Let's say there's a circle of radius r, and of this we have cut out another circle which touches the outer circle. So it has been cut out such that one end touches the outer circle, the bigger disk, and the other, the diametrically opposite end, passes through the center. Now we wish to find the center of mass of the remaining disk. So basically the region that I'm shading is the region that contains mass, and the rest has been cut out, right? So whenever you're given such a case, any general body where you have to find center of mass, always first try to see if there is any line of symmetry. In this case, you can see that this particular diameter, the one that I've drawn, is a line of symmetry. So let me call this x-axis and let me draw a perpendicular line and call it y-axis. So I can clearly see that the x-axis is the line of symmetry, right? So that tells me that the y coordinate is certainly 0, because we know the center of mass will certainly lie on the line of symmetry, right? So we need not think about the y coordinate, we can directly say it as 0. The only concern is the x coordinate. Now to do this, we'll once again use the principle of superposition. Now you already know what the principle of superposition is. Since once again we have an almost symmetric case, we'll turn it into a symmetric case. And how will we do that? This situation can be thought of as having a complete disk of radius r, and the disk that has been cut out, we'll assume that we have placed a disk of negative mass on top of this region, right? So if the part that has been cut out, if it has mass m dash, then we have kept a disk of mass minus m dash on top of it, right? So now the combination of these two should give us the same result that we will get for this disk of which another disk has been cut out, right? So before we begin this, let's try to think about the radius of this disk. You can see that this line is nothing but the diameter of the disk that has been cut out. But this line is also the radius of the original disk. So we can say the radius of the disk that has been cut out is r by 2, right? Where r is the radius of the bigger disk, right? So the first thing that we should try to do here is try to establish a relation between m dash and m, which is the mass of the original disk. Now, we can say that since we are assuming that mass is uniformly spread out, we see that mass is spread out over area, right? So mass, we know, is equal to density, area density into area. So since sigma is constant, we can say that mass is proportional to area, right? Also, we know that in case of disk, which is a circle, area is nothing but pi r square, right? So we can say that mass is proportional to radius square. Now, m dash, which corresponds to this disk, the radius is half the radius of the original disk. So if the radius gets half, we can say the mass will become 1/4, since m is proportional to square of the radius, right? So if mass is proportional to square of the radius, we can say that m dash is 1/4 of the mass, right? In magnitude, it is 1/4 of the total mass of the disk, right? Once we do that, rest of the problem is fairly obvious. We can replace these bodies with their mass kept at their respective center of masses, right? So this situation simplifies to having a mass capital M kept at origin and minus m by 4 kept at a distance of r by 2, right? Because this is where the center of mass of that negative mass disk lies, right? Right, and for the entire disk, the mass can be placed at the center of this disk, which is the origin. Right, so if you follow this, rest is fairly simple. We are trying to find the x coordinate for center of mass, which should be m1x1 plus m2x2 by m1 plus m2. So for the first body, which is the complete disk, the x coordinate is 0, so we get a 0 plus, now substitute values with suitable signs. So we'll have minus m by 4 into r by 2 divided by the total mass, which becomes m minus m by 4. So this gives you minus mr by 8 divided by 3m by 4, which leaves you with a value of minus r by 6. Now, the negative sign indicates that the center of mass is behind this origin and at a distance of r by 6. Now, this makes perfect sense because in this region, mass has been removed, right? So, more of the mass lies in this region, and hence, we expect the center of mass to shift to this side, right? Because the entire disk had its center of mass at the center. So, if you remove some mass from here, the center of mass will shift towards the left, which is indicated by this answer. So, whenever you get a result, you should always try to see if it makes sense or if it agrees with the physical interpretation of the situation that you're dealing with. Right. So with this, I think we have learned enough about center of mass. Let's move on to momentum and let's see how center of mass helps in case of momentum.